A lot of students are losing easy marks on parallel circuits without realizing why. This cleared up a lot for me.
Welcome to This Explainer. I'm absolutely thrilled you're here with us today. We're going to be tackling a topic that has, let's be honest, caused countless headaches in physics classrooms all around the world. We're talking about mastering parallel circuits and the reciprocal formula. Look, if you've ever stared down a circuit diagram, confidently punched a bunch of numbers into your calculator, and then realized your final answer was completely wrong, you know exactly what I'm talking about. Well, you are in the perfect place. We are going to break all of this down so you can finally master these calculations without the usual frustration. So, let me start by asking you a genuine question. Why do so many students completely bomb simple circuit questions on exam day? Is it because the math is just incredibly hard? Or maybe the physics concepts are just impossible to wrap your head around? Actually, no. When we look at the data and the examiner reports, it usually comes down to a few very specific and completely avoidable traps. Basically, students get tricked by visual illusions, or they forget one tiny but absolutely crucial step right at the very end of their calculations. So today, we are going to expose those traps so you never fall into them again.
Here's exactly how we're going to do it. First, we'll cover the circuit identification trap, then contrast series versus parallel circuits. After that, we'll learn the pencil trace test, dive deep into the reciprocal resistance formula, and finally, conquer that notorious final inversion mistake.
All right, let's jump straight into our first major hurdle, the circuit identification trap. The absolute biggest piece of warning I can give you right off the bat is to stop relying strictly on how a diagram is drawn. Your eyes can and definitely will deceive you. You see, the number one error students make is assuming that just because two lines are drawn parallel to each other on a piece of paper, kind of like the rungs of a ladder, that they automatically form a parallel circuit. Honestly, that is a massive misconception. A single wire can be bent to place two components side by side, but if there's no fork in that wire, they're still just connected in series. You literally cannot ignore the actual electrical path. You have to actively look for what we call the fork in the road.
And that brings us exactly to the concept of a node. A node is simply a point in a circuit where three or more wires meet, which creates a junction where the electric current actually gets a choice of paths. Finding this specific junction is the true fundamental test of a parallel branch. If the current hits a point where it literally has to divide to pass through different components and then recombines later on down the line, those components are in parallel. It's really that simple. If there's no node, there's no parallel circuit.
Okay, moving on to section 2. Let's clearly define series versus parallel circuits. We really need to draw the battle lines between these two fundamental setups because confusing their properties is another huge pitfall. Think about the pathways first. A series circuit has a single continuous path, kind of like a one-way street with absolutely no side roads. A parallel circuit, on the other hand, has multiple paths branching off at those nodes we just talked about. And because of this architecture, current and voltage behave in completely different ways. In a series circuit, the current is exactly the same at all points, but in a parallel circuit, the total current enters a junction and splits into those branches. Now, what about voltage or potential difference? In a series circuit, the total voltage from the battery is shared or split up among the components. But, and this is super important to remember, in a parallel circuit, the voltage is constant across all the parallel branches. Every single branch gets the full unshared voltage supplied by the source.
So because the current and voltage behave differently, it totally makes sense that the way we calculate total resistance is entirely different too. For a series arrangement, finding the total resistance, which we call RS, is just a simple addition rule. You just take R1 plus R2 plus R3. Pretty easy, right? But for parallel resistance, we have to use this infamous reciprocal formula. 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3. Unfortunately, a lot of students mistakenly try to use the easy addition rule for parallel branches, and well, that just immediately tanks their answer.
Which naturally leads us to section 3, the pencil trace test. How do we know for absolutely sure which formula to use? Well, I want you to literally do this physical trace test during your next exam. Step 1, place your pencil directly on the positive terminal of the battery in the diagram. Step 2, trace the path of the current toward the negative terminal. And step 3, this is where the magic happens. If you can trace the entire circuit without ever lifting your pencil or having to choose between two wires, boom, you have a series circuit. But if you hit a junction where you must choose one wire over another, like if you actually have to lift your pencil to go back and trace the other routes, congratulations, you've just found a parallel arrangement. Doing this physical motion completely bypasses that visual trap of parallel lines.
All right, we've spotted the parallel circuit. Now for section 4, the reciprocal resistance formula.
Now that your pencil trace tests confirmed we are in fact dealing with a parallel circuit, it's time to actually tackle the math. This right here is the reciprocal law of parallel resistance, straight out of the syllabus. RP stands for the total effective resistance of the parallel arrangement. R1, R2, and R3 are just the resistance values of each individual branch. But I want you to notice something crucial here. We aren't solving for RP directly right out of the gate, we are solving for 1 over RP.
To keep this from turning into cognitive overload, I highly recommend you view this calculation as two very distinct, completely non-negotiable steps. Step 1, find the reciprocal of each individual resistor. That just means writing them as fractions under the number 1 and then adding them all together. Step 2, once you have that final fraction sum, you must invert it. You flip the final result to actually find RP. Let's walk through exactly what this looks like so you can see it in practice.
Okay, so let's say we have 3 resistors, and each one has a resistance of 2 ohms, all connected in parallel. In step 1, we sum the reciprocals. So 1 over RP equals 1 over 2, plus 1 over 2, plus 1 over 2. Add those fractions up, and you get 3 over 2. Now, here is the danger zone. If you stop right here, you're essentially saying the total resistance is 1.5 ohms. But remember, 3 over 2 is equal to 1 over RP. It is not RP itself. That's exactly why step 2 is so vital. Invert the result. Flip that fraction. RP actually equals 2 over 3 ohms. If you punch 2 divided by 3 into your calculator, you get approximately 0.67 ohms. See how much smaller that is than the 1.5 ohms you would have gotten if you just skipped step 2?
And that perfectly sets up our final section. Section 5, the final inversion mistake.
I want you to listen really closely to this part, because this is, without a doubt, the single most devastating trap you can fall into during an exam. Don't forget to flip it. Seriously, I cannot stress this enough. Finding that sum of the reciprocals is only step 1. It's just the setup. If you do all that beautiful, complicated fraction math, and then you just leave your answer as 1 over RP, your final answer is 100% wrong. You're going to lose those hard-earned marks. You absolutely must take the reciprocal of your sum at the very end. Always flip the fraction. Now, because I know exam situations can be incredibly stressful, I want to give you a brilliant rule of thumb to self-diagnose if you've made that inversion mistake. You can always check your work against this one simple fact: the total parallel resistance is always less than the resistance of the smallest individual branch. Think back to the example we just did. We had 3 resistors that were 2 ohms each. The smallest individual branch is, well, 2 ohms. Our final correctly flipped answer was 0.67 ohms. Since 0.67 is definitely less than 2, we instantly know we're in the right ballpark. If your final answer turns out to be bigger than your smallest resistor, you probably forgot to flip it. It is literally a built-in safety net for your tests.
Which brings us to the final thought of this explainer. The next time you're staring down a complex circuit diagram, what are you going to do? Will you just trust your eyes, or will you use the trace test? Because your eyes are going to try to convince you that ladder rungs automatically mean parallel. But your pencil will find the nodes. Your pencil will show you the exact true path the current takes. If you apply these concrete tools, carefully sum up your reciprocals, and never, ever forget to flip that final fraction, you are going to absolutely crush these calculations. Thanks so much for hanging out with me to master parallel circuits today. And hey, I highly encourage you to go try that trace test on a practice diagram right now.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.